Now, index fossils are also used to determine relative age of rocks. Specifically speaking, if you find an index fossil in a layer of rock in one place and that same index fossil in another layer in a different place, you can say that those two pieces of rock are roughly the same age. Now, we're talking geologic time here, okay? So when we say same age, geologically speaking, we mean within, several million years of one another. Which, as far as rocks being created and destroyed, that's actually pretty short. When you're talking on the scale of 4.6 billion years, well, 0.6 billion years is 600 million years. So, this particular organism lived during, Andrew, join me. This particular organism lived during this, 10 million year period, and we found it in layers of rock all over these regions. We can say all of those layers of rocks formed during that 10 million year period. This radiometric dating is the primary method that scientists use to calculate ages of things that they haven't seen be born and die within their, lifespan. Okay, radiometric dating is also known as radioactive dating. That's what your book calls it. That's not what I will call it. Metric means measure, and so I like it better because it's a way of measuring the age of things. Okay, it's used to determine absolute ages, not relative ages. And by absolute, remember we talked a little bit about how absolute, there's still some wiggle room in there. Okay, there's some range of error in all scientific measurements. This particular measurement method, because it's looking at a time scale of billions of years, there's a plus or minus a few thousand or 100,000 or million years, but it's still closer than saying older than or younger than, which, what does that mean, really? So it does try to put some numbers on the age of things, okay? It's based on the known natural ratios of elements in certain rocks, in certain minerals, okay? And then we know the half-lives of radioactive elements, and we talked about that yesterday, how you find out the half-life of something. Today we're going to find out the half-life of M&Ms and Skittles. Yeah. Okay, these are various elements, radioactive elements, and their half-lives. Now, remember yesterday I was writing these a little differently. The number, this number was over at the left instead of the right. Fine. It's fine. Different scientists write it differently. Okay, the radioactive parent in our example yesterday was uranium-238. The radioactive daughter, the initial daughter yesterday, was thorium. Remember we talked about uranium becoming thorium? And then thorium became protactinium. Okay, so each radioactive parent has a daughter followed by another, potentially by another daughter, by another daughter. The ultimate daughter, the perfect daughter. So the great-great-granddaughter who never had any children of uranium-238 is lead-206. So by stable daughter, I mean the daughter that is no longer radioactive. Okay. So if you find a rock that has U-238 and thorium and protactinium and lead-206 and radium is actually one of the daughters as well, and you can determine the ratios of those elements in that rock, you can come up with a pretty decent age for that rock because you now know the half-lives of all of those parents and daughters. Half-life. The number one question about how radiometric dating can possibly work is how do you know what you started with? Okay, and I think we talked about that maybe a little bit yesterday. How do you know how much of something you started with? Not much.
We did a little bit.
A little bit? Okay. Rocks, as we talked about, minerals have a known chemical composition, right? So emerald has a certain amount of silicon, a certain amount of oxygen, a certain amount of copper, beryl, different things that make it green. Okay, beryllium, not beryl. In those crystal lattices, based on the size of the elements that are in them,
Why?
in those crystal lattices, different elements might occasionally substitute in. So, for example, in zirconium silicate, there are trace amounts of uranium.